Hi, I'm Rahul Anantharaman from SINTEF Energy Research, and here I'll be presenting an overview of the ACT project PrISMa, where we are developing a technology platform to tailor-make cost-efficient carbon capture solutions. I would like to acknowledge my co-authors and the team at SINTEF Energy Research who have contributed to the project. Adsorption-based processes are attractive candidates for cost-efficient CO2 capture. The development of adsorption process for CO2 capture have proceeded along two lines. On the one side, we have the material science perspective, where a large number of novel materials are under development, materials such as the metal organic frameworks, covalent organic frameworks, or mixed metal oxides. And on the other side, we have the process engineering perspective, where several process configurations are optimized to maximize the performance. This is typically done for a given adsorbent and emission source. Historically, there hasn't been much of an interface between material sciences and process engineers. So presently, there exists a gap between these two approaches. This was identified as a challenge in the Mission Innovation Workshop held in Houston in 2017. Recently, at a European level workshop on CO2 removal, combined material, process, and unit operation design was identified as a key to reduce the cost of CO2 capture. So the PrISMa project was developed to address this challenge. PrISMa stands for Process-Informed Design of Tailor-Made Sorbent Materials for Cost-Efficient CO2 Capture. PrISMa is an ACT project that started in 2019. PrISMa brings together 4 research groups with complementary expertise to address this challenge. The project is led by Heriot-Watt University. The other project partners are EPFL, University of California, Berkeley, or LBNL, and SINTEF Energy Research. ETH is in the process of joining the consortium and will bring their expertise on environmental assessment in the project. The core of the PrISMa project is the PrISMa technology platform, as shown here in this figure. The PrISMa technology platform takes into consideration CO2 sources and CO2 sinks and identifies the most promising materials for a given specific application. By the given application, we mean a combination of a source and sinks. It achieves this by bridging molecular simulations with process modeling to screen thousands of adsorbents, which is done with screening models developed in the first part of the platform, and ranks them for a given performance metric. The performance metric here in PrISMa is the ECP, or the effective carbon price. Effective carbon price is a modified CO2 avoidance costs, where we have included some aspects of the CO2 source and sink, which are traditionally not considered in the CO2 avoidance cost. So once these promising materials have been identified with the screening tool, the materials are then synthesized, the most promising materials are then synthesized and characterized. They are further performance tested for the intended carbon capture application. This allows validation of the models, and the potential of the material process combination is identified that makes the technology cost competitive. So the results of the material characterization, where more information is available about the materials, so this information is then fed back into the models to improve the models and validate them further. The detailed material characteristics are now included in full physical model, where case studies are performed to bring the technology to TRL5. The key technical outputs of the project are 2. The first one is a technology platform that we've talked about, which is based on a methodology for systematic knowledge exchange between material science and process engineering. And the second one are a set of case studies to bring the technology material to TRL5. So the first step in the process is the development of a screening tool. The goal is to screen promising absorbents that give the lowest ECP, or effective carbon price. Here it is critical to link the material properties with the process and economic key performance indicators, or KPIs, shown here, and then further link them to the ECP. Here you can see in this figure how the different process and material parameters are interlinked. The idea here with this slide was to show that we talk about ranking the different adsorbents according to the ECP, effective carbon price, and then linking them back to the material properties. But it is to indicate that this is not a straightforward link back to material properties, but it is a complex process to get back to the material properties. So the objective of the screening part is the development of a techno-economic computational screening tool for translation of process KPIs into property targets for material design, as I talked about earlier. So to do a good screening, we cannot use the full physical models, which are very computationally expensive, because we are trying to screen thousands of adsorbent materials here. So what we need are models that can rank these adsorbents in the right order of priority, but at the same time are not computationally expensive. So to do this, we followed a systematic methodology of developing these models that are systematically increase in complexity, that provide higher accuracy. So we start with the thermodynamic equilibrium model, which is the basic model and is developed for both the PSA and TSA, and these models are available in the open literature. In the next level, we add non-ideal effects such as mass and heat transfer resistance and pressure gradients to allow a more realistic representation of the system, and also to provide inputs for the techno-economic analysis. The next level is to add process parameters such as the cycle configuration and vacuum pump efficiency to include the impact of the process and allow co-optimization of materials and processes. In parallel, we've developed the techno-economic models that link the output of the screening model to the effective carbon price. So at each level of computational complexity and accuracy that we have, we can get a techno-economic model that links these models to the ECP. So once we have these screening tools, they are used in the screening workflow, where the inputs are case study, source, and sink characteristics of CO2, adsorption properties that are got from molecular simulation, both physiochemical and adsorptive properties, and parameters for optimization. And the output is where we're ranking of these adsorbent materials. So as I said earlier, the screening output is a ranking of absorbents based on the ECP, or effective carbon price. So using this, we can identify the most promising adsorbents. But not only that, this is also used to identify target ranges of key parameters or material properties to identify ideal adsorbents. We have been working since the project started to set up this platform to screen thousands of materials. We are starting to generate results now, and the first proof of concept results for 50 adsorbents will be presented at GHGT in March, and we are in the process of writing the paper for the conference right now, which is due next week. We'll subsequently start screening for the large database of thousands of materials once we get the proof of concept done. So I'd like to finish off by emphasizing the innovative approach that we use in PrISMa. Once we take the screening, which is a combination of material science and process engineering, to identify promising candidates, these are synthesized and characterized in the lab, and then the detailed material information that is available after the synthesis and characterization is used in full physical models, which are computationally intensive, and they are used to develop detailed performance analysis of the adsorbent processes in the selected case studies and benchmark them against other solutions. So with this, I would like to end my presentation. Thank you very much.